Good morning. Today onwards, I'm trying to share a few lecture videos on the subject Geotechnical Engineering 1, which pertains to Kerala Technological University KTU syllabus. And the contents which the university expects us to cover includes the introduction to the subject, the three-phase system diagram and the relationships, the index properties and classification of soil, permeability of soil, effective stress principle, consolidation of soil, compaction of soil, shear strength of soil, slope stability. Now, though we would deal with things which are expected to be in a laboratory section, for example, first module covers the sand replacement and field density method, I have not listed every detail in the contents here. I've made a very crisp list of contents, and which starts with the introduction and goes all the way down to slope stability. Now, compared to the previous syllabus that KTU had prescribed, the two differences which comes to my mind is, number one, the module number was up to 6 previously and now it has got shrunk to 5. Plus there has been a rearrangement in the topics and the flow scheme of things. But anyways, coming to the introduction, those who are in your second year would be interested to know these things. Others may skip this. What are the branches of civil engineering? Now, the branches of civil engineering, the masters that you can probably pursue after your bachelor's degree, includes structural engineering, geotechnical engineering, transportation engineering, water resource engineering, environmental engineering, etc. Not limited to the list I've mentioned here. Of course, you have other branches as well, disaster management, geographical information systems, etc. But the ones that are popular, at least in our country, at least in our state, is structural, geotechnical, transportation, environmental, water resource, etc. So in that scheme, where does geotechnical engineering fits in? Geotechnical engineering, as the name suggests, is nothing but soil mechanics. So earlier the subject was called as soil mechanics and foundation engineering, and SMFE as it was abbreviated. Soil mechanics deals with the basic nature of the soil as a material, and foundation engineering deals with how the soil will behave under loads. For example, when you construct a foundation and a building over it, the load has to be transferred to the soil. The soil should be strong enough to transfer the load within the settlement criteria. So fundamentally, you have two things, soil mechanics and foundation engineering, where soil mechanics is covered in Geotechnical Engineering 1 in this particular semester, and subsequently in the next semester you will have to deal with foundation engineering or soil mechanics 2. So you can see three figures here: sand, silt and clay. Now all these three things are called soil. So in the first slide itself we can see that three different soil would be looking in three different pattern, color, texture, etc. In short, soil is uncertain in nature, and you need to have a clear difference between, you need to understand the clear difference between sand, soil and clay. Of course, the syllabus is expected to be covered in 42 hours, etc. But in the offline mode, we hardly got more than 40 hours. But I'm sure in the online mode, the one that we are in, we do have the luxury of time to cover each and every point in detail, and we can expect to complete that in, let's say, 40 or 42 hours, which probably may span across for more than 5 hours or 6 hours of online videos. The 4 modules in general is, the first module will cover the introduction to the subject with the general terms based on the three-phase system diagram, whereas from the second module you start with what is called as an index property of soil, and third, fourth, 5 modules are dealing with the engineering properties. I've listed 6th module here because this particular slide was prepared for the previous syllabus prescribed by the university, which had 6 modules, and now we have everything combined together and spread across in 5 modules. So nonetheless, in general, the flow is like the general properties, then you have the index properties, and then you have the engineering properties. Now there comes a term called three-phase system diagram and the relationships. Now the three-phase system diagram can probably be best explained using these 3 figures: a glass full of water or liquid, a glass which is empty, and a glass which is half full or perhaps half empty. So like I said in the online meeting, or the one that I had with my students, you can have an optimistic view about this, the last figure, saying that it's half full, or you can have a pessimistic view about it, saying that it's half empty, or you can have a realistic view about that, because you can consider that to be totally full with gas and liquid. Technically it's completely full, right? So three-phase system diagram is something similar. When you consider soil as a material, it has 3 phases. Number 1 is solid, number 2 is liquid or water, and number 3 is the air. So in its inherent condition, soil will have the particles within which you can find the void spaces, and a portion of this void space could be filled with water and a portion could be empty. Technically empty means it is of air. So I can segregate this texture into 3 layers or 3 phases. Number 1 is solid, number 2 is water, and number 3 is air. So this representation for easiness is called as 3-phase system. So in short, you have generalized the soil as a set of 3 phases: solid, water, and air, for our easiness of derivations and relations. And when you completely empty water, and once you have completely expelled water out, what remains is just the solid and the air. So that case is a totally dry soil. Whereas when the voids are completely filled with water, this figure will not have air here. You just have solid and water. So that's a fully saturated soil. Everything else which falls between fully saturated and dry soil will be partially saturated, which means you have 3 phases: solid, water, and air. Now, once you understand the 3-phase system diagram, the flow goes to the permeability of soil. Soil as a material is permeable. So permeability of soil is the property with which it allows water or any fluid in general to pass through it. This figure shows concrete as a material being permeable. Likewise, soil again is permeable. And in this module of permeability of soil, you'll have to deal with the Darcy's law, based on which you have a few derivations and a few relations. So in short, permeability of soil is based on Darcy's law's definition in its very crude and basic format, but you have got different other theories as well. The next one is about index properties and classification of soil. In this figure you can see that, of course, these are figures taken from the internet, and in this figure you can see that the types of soils are classified based on the size. You can see pebbles up, and then you can go up to 200 micron sizes and 100 micron sizes, etc., which turns out to be too powdery and fine soil. So this palette offers you different sizes of soil, starting from pebble size up to very powder size. So it's just a classification based on size. You can have different classifications based on other criteria as well. So index properties and classification of soil is very important. Indexing means that you are having some properties based on which you can identify soil as a material, just like the index that you have for your book, textbooks, etc. Once you go to the index page, and once you go to the index page, you can find your target of interest based on the page numbers, etc. So indexing of soil will help you to classify the soil, and classifying of soil is very important for you to convey an idea about the behavior of soil. Next comes the effective stress principle, which is a module based on which you mix the fundamental soil mechanics of stress is equal to force by area and define the behavior of soil under stress or pressure. Then you have shear strength of soil. This is a very important property of soil which governs the behavior of a slope or bearing capacity of foundations, etc. So when you talk about stresses, you would be familiar with three different types of stresses. Number one is tensile stress, where an axial pull-out load is applied. Number two is a compressive stress, where a compressive load axially is applied. And number three is a shear stress, where a tangential stress is applied. Now, in tensional stress, the best example would probably be steel rods or iron bars. Iron and steel are designed to take tension, whereas concrete as a material is designed to take compression. Likewise, shear strength is a strength that defines soil as a construction material. For example, let's take a slope here. So when you have the slope, you have the force of gravity acting in the downward direction, and you have a component of which acts in along the slope direction. So a component of the gravity force would induce a shear stress, and once the shear stress exceeds the maximum limit a soil can take, the soil will fail. So these naturally occurring calamities, including the landslides and soil instability, slope instabilities, are fundamentally based on the property of shear strength of soil. Again, when you have a load or a foundation or a building kept above the soil is under compression, but that compressive force along an inclined plane will act as a shear force. So in short, shear strength is a very important property of soil. Then you have what is called as a consolidation. Consolidation, as the name suggests, is bringing together particles. Let's take the example of a sponge dipped in water, and once you try to squeeze the sponge, water of course expels out. Quite similar to that, when you have a saturated soil and when a load is applied on a saturated soil, it behaves quite similar to that of a sponge, and water expels out. When water expels out, the voids within the soil granular matrix decreases and the soil settles, which leads usually to cracks on buildings. So in this particular case, again a photograph taken from the internet, you can guess that the soil beneath this portion may have settled, and which may probably be due to the consolidation settlement, and the building starts to develop cracks. Another example of importance of slope stability is shown in this picture. Slope stability. This is included in your syllabus as well. So slope stability, the different theories which may help you to analyze the stability of slopes, the factor of safety, etc., are covered in this module. Then you have what is called as compaction of soil. Again, it's an engineering property which comes under the compressibility. So when you compare compaction and consolidation, compaction is an artificial process in which you may have different rollers, or you may have different dynamic compactors like this, which you use to increase the density of the soil at the site. So once you increase the density of the soil, the engineering behavior of soil would be better. Consolidation, on the other hand, is usually a naturally occurring process. A saturated soil, when induced with force, settles due to the expulsion of water, whereas in compaction, you artificially generate a stress above the soil, thereby decreasing the volume of the soil and increasing the density. So these are in brief the different topics that you should cover in your Geotechnical Engineering 1 course, and I've listed a few tips to enjoy the process here, which would help you fetch marks had it been a usual classroom learning. Thank you.